So in this video we are going to discuss the question in thermal and statistical physics which appear in JRF examination that occurred in December 2016. So let's continue with the first question. The question is a silica particle of radius 0.1 micrometer. So we are given a particle whose radius is 0.1 micrometer. 0.1 micrometer, or this can be written as 0.1 into 10 power minus 6 meter. Okay, it's put in a container of water at temperature T. So temperature is given to be 300 Kelvin. So that means the particle at this temperature will have certain energy that depends upon this given temperature T. Okay, so the densities of silica and water are, so that means let's denote the rho silica, that is equal to silica and water are, it is 2000 kilogram per meter cube, and water is equal to 1000 kilogram per meter cube. Okay, due to thermal fluctuations the particle is not always at the bottom of the container. Okay, the average height of the particle above the base of the container is approximately. Okay, so let's try to understand this problem with the help of a diagram. Okay, so we are having water inside the container, and here we are having a silica particle. Okay, if at certain non-zero temperature, because of the the non-zero value of the temperature, so this particle will have certain thermal energy which is which further depend upon the temperature. Okay, so that means let's say the average height which is acquired by this particle due to the thermal energy, that is that is H. Okay, so therefore the potential energy of the particle at this height is equal to the potential energy of silica particle at height. This is the average height, you can say, H, that is equal to the mass of the particle, then acceleration due to gravity, and the height above the ground. Let's call this as equation 1. Now due to the temperature T, the average thermal energy of the particle will be the average thermal energy of the particle, that is equal to 3/2 kBT. It's 3/2 kBT because particle is independent to move in all three different directions. Okay, so now the average height which is acquired by the particle, that depends upon basically the amount of this energy. Okay, so that means the height we can obtain by simply comparing equation 1 and 2. Okay, so therefore mgh, that is equal to, that's the average potential energy, and that should be equal to average thermal energy, which is 3/2 kVT. Okay, so from here we obtain H is equal to 3/2 kVT upon mass of the particle and acceleration due to gravity. Note that the mass of the particle can be immediately determined from its density and its volume. So where rho silica multiply by the volume of the particle. Okay, so therefore H is equal to 3/2 the value of the the Boltzmann constant, which is 1.38 into 10 power minus 23 joule per Kelvin, and then multiply by the temperature, which is 300 Kelvin. It's given to us in the statement. Okay, divided by mass of the particle, which is given by the product of these two quantities. Okay, or rho silica is given to us as it is 2000 kilogram per meter cube. Okay, so that means 2000. Okay, this is rho silica into volume. Rho, that is 2000 into the volume is 4/3 pi r cube. Okay, pi, well, you can take 3.14, and then r cube is the given radius, which is 0.1 into 10 power minus 6, which will become 10 power minus 7 meter basically. So 10 power minus 7 cube, and then multiply by the acceleration due to gravity. Okay, the acceleration due to gravity, it is 9.8 meter per second square. So here we are taking g, that is equal to 9.8 meter per second square, and this after evaluation, this you will note that this comes out to be equal to 3 into 10 power minus 4 meter. Okay, so therefore B is correct here. So let's take a look at the next problem. The statement is the partition function of a two-level system is governed by Hamiltonian, which is given by this expression here. Okay, so in principle we can determine the partition function for the given system by simply knowing the energy eigenvalue for the given Hamiltonian. So let's try to understand how we can determine the energy eigenvalues for this particular case, and then immediately we will be able to write the expression for the partition function. Okay, so the energy eigenvalues, they are determined by knowing the characteristic matrix, which is written as H minus lambda I, that is equal to gamma minus delta and minus gamma. Okay, minus lambda I, that's unitary matrix, and this will give us, after multiplication we will obtain gamma minus lambda minus delta and then minus gamma minus lambda. Okay, and the characteristic equation is from here. The characteristic equation is given by H minus lambda I equal to 0. Okay, this implies gamma minus lambda minus delta minus gamma minus lambda and its determinant, that should be equal to 0. And after solving we will obtain by okay, so that can be done simply. After solving we will obtain minus gamma square minus gamma lambda plus gamma lambda plus lambda square minus delta square, that is equal to 0, and this gives lambda square is equal to gamma square plus delta square, which implies lambda is equal to plus minus gamma square plus delta square. So therefore the energy eigenvalues are, therefore energy eigenvalues are E1 is equal to gamma square plus delta square under root, and E2 is equal to minus of gamma square plus delta square. Okay, so by knowing these two energy eigenvalues we can immediately determine the partition function. So you can call this as E2 and E1. Okay, so therefore the partition function is Z, that is equal to exponential minus beta E1 plus exponential minus beta E2. Okay, and that is equal to exponential minus beta into gamma square plus delta square power 1 by 2 plus exponential beta into gamma square plus delta square power 1 by 2, or this is further equal to 2 cos hyperbolic beta under root gamma square plus delta square power 1 by 2. Okay, so therefore the correct option here, which is matching with our result, that is option B. So B is correct here. So this is a slightly different question that we usually handle while finding expression for the partition function. So let's take a look at the next problem. The statement is, consider a gas of n classical particle in two-dimensional square box of side L. Okay. So if the total energy of the gas is E, the entropy apart from an additive constant is. So we have to find the expression for the entropy of the gas in terms of energy E. Okay. So let's try to handle this problem. So because the particles, they are given to be classical. Classically the particles are treated as distinguishable. But later on, in order to, in principle, the particles, they are not distinguishable, they are indistinguishable. So therefore, to take into account the indistinguishability of the classical particle, we do certain change in the calculation of the partition function. So therefore, in principle, particles are indistinguishable. Okay, and this has important consequence on the evaluation of the partition function. Okay, so for n particle system, the partition function is given by 1 upon n factorial and h power 2n here, because here we are talking about a two-dimensional system. If it's the problem is in the three-dimensional system, then we might have divided by h power 3n here. Okay, so depending upon the dimension of the system we are talking about, accordingly we have to divide by a appropriate factor here, and then exponential minus beta e, and then dq 2n and dp 2n. Okay, if this problem was in 3 dimensions, then we might have written here dq power 3n and dp 3n here. Okay, and that is equal to z1 power n divided by n factorial. So that means in principle, if somehow we are able to determine the partition function for one single particle, then we can immediately determine the partition function for the n particles. Okay, so for n is equal to 1, let's say. So first of all, let's determine the partition function for a single particle. So for n is equal to 1 in 2 dimension, in 2D, okay, d2q, that is equal to L square, and which we will call as area. Okay, similarly in 2 dimension, d2p, that is equal to 2 pi p dp. Okay, so with this information we will write the partition function for a single particle as it's 1 by n factorial, that will give us 1 for n is equal to 1, and then 1 divided by h power 2 integral exponential minus beta e, and then we will have a d2q, that will give us L square basically. So I am writing L square for the space integral, and then the integral over the momentum, that's d2p, so that will give us 2 pi p dp. Okay, or that can be written as 2 pi L square, keeping the constant terms outside, 2 pi L square divided by h square, and then inside the integral we will have exponential minus beta e p dp. So let's call this as equation 2. Okay, now because here in the exponential we are having energy E, so we will also transform p dp in terms of energy. So let's see how we can do that. We are having the momentum energy relationship as p square by 2m, that is equal to E. Note that here p square is equal to, because it's a two-dimensional problem, p square is equal to px square plus py square. Okay, so p square by 2m, that is equal to E. So this implies 2p dp divided by 2m, that is equal to dE. Okay, so which further indicate that dE that is equal to P dP by m, P dP by m. Okay, so therefore with this information I can rewrite the partition function as Z1 this is equal to 2 pi L square upon h square, and then the integral from 0 to infinity, okay, exponential minus beta e this point, and then P dP. Okay, so P dP will be equal to MDE. So from here, so P dP that is equal to MDE. Okay, so this is equal to 2 pi L square m upon h square exponential minus beta e upon minus beta from 0 to infinity. Okay, and this after evaluating the limits from 0 to infinity, this comes out to be equal to 2 pi m L square upon h square into 1 by beta. So let me call this as equation 3. Okay, so therefore for n particles confined in 2 dimensions, Zn will be Z1 power n divided by n factorial. Okay, so this is equal to 1 upon n factorial, and inside the bracket we have Z1 which is 2 pi m L square upon h square into 1 by beta and its power n. Let me call this as equation 4. Now from here we can easily determine the average energy per particle, because at the end we require this expression. So that's why we need to determine the average energy, and that is given by the average energy and the partition function. They are connected as the average energy E per particle. Okay, so I'm writing this as E1. Okay, that is equal to if you want to determine it for the n particles, so then you can directly use the partition function for the n particles together. So this is equal to minus curly beta of Zn. Okay, and for if we use the expression for the single particles, then this is minus curly beta of ln Z1. So let's make use of it, and then we can determine this by simply multiplying the the average value per particle with n. Okay, so this is equal to E1, the average energy per particle, that is equal to minus curly beta ln 2 pi m L square upon h square into 1 by beta. Okay, so therefore this is further equal to h square beta, it's 1 by x. Okay, so h square beta upon 2 pi m L square, and then its differential with respect to beta. So then we will then its differential with respect to beta. So then we will have 2 pi m L square upon h square, and the differential of beta the differential of 1 by beta with respect to beta. So that will give us minus 1 upon beta square. Okay, and that is equal to, this is with negative sign, minus curly beta. So this minus and this minus will become plus, and that is equal to 1 by beta, or that is equal to kBt. So therefore for n particle system, average E that is equal to n multiplied by the average energy per particle, that is equal to n kBt. Okay, so let's say this is equation 5 here. Okay, now our ultimate target is to find the expression for the entropy. So in order to determine the entropy, first we need to find the Helmholtz free energy for the system. Okay, so now the Helmholtz free energy, written as A, that is given by A, that is equal to minus kBT ln Zn. Okay, so that means that is equal to minus kBT ln 1 over n factorial, and then inside the bracket we have 2 pi m L square upon h square into 1 by beta, okay, and its power n. Okay, and this upon expansion will give us, while expanding, so we can rewrite this as A is equal to minus kVt, and inside the bracket we will have, because it is ln 1 upon n factorial, so that will be equal to minus ln n factorial plus, so n I will take before the logarithmic, so n ln 2 pi m L square upon h square beta. Okay, so we are simply expanding the expression. Okay, and this can be for the, so here we will apply the Stirling approximation, because n in when it's large, so apply the Stirling approximation, then we can expand it. Okay, so by doing that, so this is equal to minus kVt, and then apply the Stirling approximation, minus n ln n, and minus minus will become plus n. Okay, plus n ln 2 pi m. So I'm going to replace beta with kt. Okay, so 2 pi m L square upon h square multiply by kt, kVt basically. Okay, I have replaced beta with 1 upon kVt. Okay, and this is equal to, because kt, so we will make use of the this definition, equation 5. From equation 5 we notice that kt is equal to E by n, because ultimately if you just take a look at the options which are given to us, they are in terms of energy, they are in terms of energy. Okay, so that's why we have to transform our result accordingly. So here instead of kVt, so I'm going to replace this kVt with E by n. Okay, so therefore I can rewrite this as, this is equal to minus nkt, sorry, it will become plus, so this is equal to n kVt ln n, and then the next term minus n kVt, and then the last term, that is equal to minus n kVt ln 2 pi m upon h square, and then L square, and then kt, as I said earlier, kt is equal to E by n, E upon n. Okay, because kt is equal to E by n. So okay, so now from this expression, let me call this as equation 6. Okay, so from here I can immediately determine the entropy, that is S is equal to minus dA by dt, by keeping other parameters n and v constants. Okay, and that will give us, so differentiate this expression with respect to t by keeping rest of the parameters constants, and this is equal to from the, well, okay, it was n kt, not n kv ln, so there should be t here again. Okay, so okay, so when we differentiate with respect to t, so we obtain minus L, the first term is minus n kb ln n, and then differential of the second term with respect to temperature, that will give us plus n kb, then differential of the third term. Okay, so with respect to temperature, so that is equal to plus n kb ln 2 pi m upon h square L square Ey n. Okay, and this can be further rewritten as minus n kb ln n plus n kb plus n kb ln 2 pi m upon h square plus n kb ln L square E upon n. So basically we splitted this the last logarithmic term here. Okay, and this can be further rewritten as n kb ln n. This is basically equal to, so we can club all these terms in one single terms. Okay, so if we call this as S0 plus n kb ln L square Ey n. Okay, or this is equal to S0 plus 2n kb ln L under root E upon L under root E upon, let me check if I'm not doing any mistake, L under root E upon n, is it? So that will give us, yes, L under root E upon n. Okay, actually, okay, it was n square, so ln n. Okay, so earlier it was, so we n kb ln n. So this factor, okay, this factor basically when absorbed here in the last terms, that will give a n, the factor of n square here. So ultimately we will be left with L under root E by n and its square, so that power 2 will come here. Okay, so that means therefore the correct option is S is equal to S0 plus this term. Okay, so then if we just compare with the options which are given to us, so they are it is C, 2n kb ln L under root E upon n. So therefore option C is correct here. Okay, so therefore C is correct. So let's continue with the next problem. The statement is, an atom has non-degenerate ground state and doubly degenerate excited state. Okay, so that means let's draw the energy spectrum of the atom. So it's a G is equal to 1 and G is equal to 2. Okay, and further the energy difference between two states is E. Okay, so let's assume this is 0 and this is E, so that the difference become E. The specific heat at very low temperature such that beta is much greater than unity, beta E is much greater than unity, is given by. So we have to obtain the correct expression for the heat capacity at constant volume with the given information. Okay, so we can handle this problem by first determining the partition function for the system, and then from there we will evaluate the average energy. Okay, so let's try to first find out the expression for the partition function for the system, and which is given by Z, that is equal to Gi exponential minus beta Ei. Okay, so since we are having only two energy terms, so G1, that is equal to 1 exponential minus beta E0 minus beta multiplied by 0, okay, plus G2, which is 2 exponential minus beta E2, which is E. So this is equal to 1 plus 2 exponential minus beta E. So that's our partition function. Okay, let's call this as equation 1. From here the average energy of the system is E, that is equal to minus curly beta of ln Z, and that is equal to minus 1 upon 1 plus 2 exponential minus beta E, and then the differential of this term with respect to beta, twice exponential multiply by 2 exponential minus beta e and multiply by minus e. Okay, so this after solving becomes 2e exponential minus beta e upon 1 plus 2 exponential minus beta e. Okay, and this can be further rewritten as 2e, taking exponential multiplying the both numerator as well as denominator with exponential beta e. So this becomes 2e upon exponential beta e plus 2. Okay, so this is equation 2. Okay, now the heat capacity is given by Cv, that is equal to dE by dt at constant volume. Okay, so that means this is further equal to 2e. I will keep it outside because e it's fixed basically. Okay, so then the differential of 1 upon exponential beta e plus 2. Okay, so after doing the differentiation, that g f dash minus f g dash, so g f dash is a constant term, so that will give a factor of 0. Okay, so therefore minus 1 minus f g dash, so minus 1 into g dash, so that is differential of this quantity, so exponential beta e. Okay, and then it's with respect to temperature, so E y kVt, differential of E y kVt will give us minus E y kVt square. Okay, and divided by exponential beta E plus 2 its whole square, g f dash minus f g dash upon g square. Okay, now we have to adjust the terms here in this expression, so I can rewrite this as Cv, that is equal to, so I will take the common terms outside, 2 kb E upon kVt square exponential beta E upon exponential beta E plus 2 and its whole square. Okay, so now we will make use of the approximation which is given to us, because it's given that beta E, which is equal to E upon kVt, it is much greater than unity. So this implies e power beta E plus 2, that can be approximately rewritten as exponential beta E. Okay, so under this approximation I can rewrite Cv, that is approximately equal to 2 kb E upon kVt square, and then applying this approximation here in this expression, this comes out to equal to exponential beta E upon exponential beta E its square, and that is almost equal to 2 kb E upon kVt square exponential minus beta E. Okay, so that's the final expression for the heat capacity under the approximation beta E, that's much greater than unity. So therefore the second option is correct, sorry, the C option is correct here. So let's take a look at the next problem. It is related to random walk. So the statement is, consider a random walk on an infinite two-dimensional triangular lattice, a part of which is shown in the figure below. Okay, if the probabilities of moving to any of the nearest neighbor sites are equal, okay, what is the probability that random walker returns to the starting position at the end of exactly 3 steps? Okay, so what we are going to do is we are going to fix a point as our origin. Let's say this is our origin O. Okay, so now the way probability is defined is, it is the probability that is equal to the favorable outcomes divided by total outcomes. Okay, so when the random walker is taking the first step, so at point O, step 1. Okay, so let's take a look at the situation. So when the random walker is at this position, he is having 6 different options to take the first step or to execute the first step. Okay, so let's say I'm denoting all these 6 different options by these arrows. Okay, so out of these 6 steps, the random walker can move in any particular direction. So let's choose any one of the direction. So let's say the random walker has started from this point and he took the first step along this direction, and let me label this point as A. Okay, O to A. So let's determine the probability of taking the step 1. So we are having favorable steps. They are also 6. Okay, and the total steps or the total path, you can say they are also 6. Okay, so all of these 6 different paths, they are equivalent. Okay, so the relevant probability for the taking the step 1 is P, the probability for taking the step 1, that is equal to the favorable outcomes, which are 6 here, divided by the total outcome, which is also 6 here. So this is equal to 1 for the first case. Okay, now as I said that if we assume that the random walker has moved along the direction O to A. Okay, now again at this point we have to identify the total possible outcomes of taking the steps, and then the favorable outcome. So at point A, that is step 2. Okay, so the total steps are the total path available to the walker. Total paths are which are available to the walker. Again, they are 6. How? So either the walker can move along this direction. It's exactly the same way as at point O. Okay, so these are the 6 different options. Either he can move in the forward direction or backward direction also. So here again total paths will be 6. But now the question is, what is the the situation that is given to us, that the random walker has to take exactly 3 steps and again come back to the point O. So total paths, they are 6, but we have to now figure out the favorable path. Okay, so let's try to do that. Favorable paths. So at point A, if random walker move in this direction, I mean, okay, so so then the random walker will never be able to move to the point O after just taking up one more step. Okay, because we have to only allow the 3 steps to the random walker. Okay, but whereas if the random walker move like this along this line, again he will not be able to come to the starting point in exact 3 steps. Okay, so this way we notice that the only options that are left with the random walker is that the lines where I have drawn 2 arrows, these are the only 2 favorable paths through which the random walker can again come back to the same starting point O with exact 3 steps. Okay, so the favorable path at point A are 2 basically. Okay, so the probability of executing step 2, that is equal to the favorable path, which is 2 divided by the total number of paths. Okay, now when the if we assume that the random walker has moved from point A to point B, let's say now the walker has moved to point B here. Now the walker is at this position. Okay, so at this point again we will identify the possible the favorable path and total path. So at point C, that is execution of step 3. Okay, so again the total paths will be 6, but out of these total 6 paths, what are the favorable paths? So let's take a look. Favorable paths. So when the random walker has reached at this point, okay, at point B, and because now it's going to third step, and in third step random walker is assumed to be at point O. So there is only one possibility or one possible path by which the random walker can again come back to the same original or the starting position. Okay, so therefore the probability of execution of step 3, that is equal to the favorable path divided by the total path. Now the net probability is given by the product of all these three the probabilities, that is probability of executing step 1, probability of executing step 2, and probability of executing step 3, and that is equal to 6 by 6 multiplied by 2 by 6 multiplied by 1 by 6. So 6 will cancel with the 6 and this will cancel with so we are left with sorry, it's 2 by 6. So this is equal to 1 by 18. So therefore option C is correct here. So let's continue with the next problem. The statement is the electrons in graphene can be thought as a two-dimensional gas with a linear energy momentum relationship, which is given like this: E is equal to PB, where P is a function of Px and Py, because we are talking about a two-dimensional system here, and V is a constant. If rho is the number of electrons per unit area, so it's given that rho, it represents number of electrons per unit area. The energy per unit area is proportional to. So we have to find the dependence of the energy on the number density. Okay, so let's see how we can handle this problem. So what is given to us is, so let's first take a look at the things which are provided to us. So we are given the dispersion relationship, which is E is equal to PV. Okay, where V is a constant and P, it's a function of Px and Py only, which merely indicates that it's a two-dimensional system, and also given that V is a constant. Okay, because graphene, it's a two-dimensional system. Okay, so now in order to solve this problem, we must have an idea about the density of states basically. Okay, so for this we will follow the approach that we have already discussed in the classroom. The density of states in two dimension is given as, I'm talking about the density of states in a certain energy interval, E to E plus dE basically. Okay, so GE dE, and that is equal to GP dP. And the reason is that because it doesn't matter whether we are writing the density of states either in the momentum interval or energy interval, but their number it's going to be same. Although the expression might differ to a certain extent, but the number will come out to be exactly equal. Okay, and this will be equal to the degeneracy factor, okay, multiplied by the available phase space volume. You can say in 3 dimension it's the area in 2 dimension. So it's the ordinary area multiplied by the area in the momentum space, that will be pi p square. But because we are talking about the momentum range or the energy range, so basically from this expression we will obtain by taking its differential with respect to p, so we will obtain 2 pi p dp. Okay, so when we differentiate it with respect to p, so then we obtain the density of states over the momentum interval p to p plus dp, or in other words in the energy interval E to E plus delta E. Okay, so here I'm going to write 2 pi p dp and divided by the volume of one unit cell in the phase space, that is h square. Okay, so let's call this as our equation 1. Okay, now we are also given that actually we want to transform this expression equation 1 in terms of energy. Okay, and that we will do with the help of the given dispersion relationship E, that is equal to PV, which implies P is equal to E upon B. This is the standard procedure that we have already adopted while talking about the theory. Okay, so from here dP that is equal to dE upon V. Okay, now we will make this substitution in equation 1 and then see what we are obtaining is. So therefore GE dE that is equal to GS, that's a degeneracy factor, and then the remaining term GS A into 2 pi A upon H square, and then 2 pi and P is equal to how much? That is E by B, and then multiply by dP, P and then dP. So what is dP? dP is dE by V, dE upon B. Okay, so this turns out to be equal to GS, the degeneracy factor, and then 2 pi A upon H square nu square, sorry, not nu, it is B, sorry, it's B square E dE. Okay, and here let me just talk about a GS also. It's a spin degeneracy factor. Basically it's equal to S plus 1, because for spin half particle this will come out to be equal to 2 when we take S is equal to 1 by 2. Okay, so okay, so now with the help of this expression, this is the required expression for the density of state over the energy interval E2 E plus dE. So let me call this as equation 2. So with the help of this expression for the density of states, we can evaluate the total number of particle or the fermion in the system. So n that is equal to 0 to EF. If we are talking about a system at absolute 0, so then we need not worry about the energy level beyond Fermi energy, and then multiply by the Fermi Dirac the probability distribution function Fe. Okay, and then multiply by the GE dE, the density of states. Okay, GE dE, and this will give us the total number of electrons. So now recall that while we discuss the properties of this Fermi Dirac probability distribution function, which is given by Fe that is equal to 1 upon 1 plus exponential E minus Ef upon kT. So when we talk about the absolute zero temperature, so the property of this function is such that its value, its unity at absolute 0. Okay, so if we plot this function along y-axis f of E, and this is the energy. Okay, so and this is the situation at EF. So below EF, the value of this probability distribution function, it's unity, and beyond EF it vanishes, it's 0 here. Okay, so that's why, because we are performing the integration from 0 to EF within the up to the Fermi level, we are talking about a system at absolute 0. Okay, then we will take its value to be equal to unity. Okay, and then we will substitute GE dE from equation 2, and let's see what we are obtaining is. And also instead of GS we will take a factor of 2 here as a spin degeneracy factor. So our expression for the total number of fermion or the electrons in this system, that comes out to be equal to 2 if I am taking GS is equal to 2, so 0 to EF, and then 1 for the Fe, that's the probability distribution function, and then 2 multiply by 2 pi A upon H square B square E dE. Okay, so this comes out to be equal to 2 into 2 pi A upon H square B square and EF square by 2 after the plugging the value of the limits. Okay, so this 2 will cancel with 2. Okay, so therefore the number of fermions in the system, that is equal to A upon 2 pi multiply by EF square upon H cut nu square. So here I have changed H into H cut, so that's why we are having a factor in the denominator, factor of 2 pi in the denominator. Okay, let's call this as equation 3. Okay, so this equation 3 implies that EF square, this equation implies that EF square, that is equal to 2 pi h cut square b square into rho, where I have written n by a as the electronic density, that's the number density, also called as number density. Okay, so let me call this as equation 4. Now we want to determine the average energy at absolute zero. Okay, so the average energy at 0 Kelvin, so that is given by E average, or like this, E average, and that is equal to, so we will follow the standard definition of evaluating the average of a physical quantity, that's 0 to EF, because we are doing the evaluation up to the Fermi level, and then the physical quantity itself, and then the probability distribution function f of E, which is in principle equal to unity, and then multiply by the density of state, GE dE divided by Fe, the probability distribution, and then the density of state, GE dE, and integration from 0 to EF. Okay, and if you do that, because this is equal to unity, okay, here also we will put it unity, and this is equal to 0 to EF E GE dE divided by GE dE from 0 to EF. Here also it's from 0 to EF. Okay, if you just take a look at the denominator, so the denominator will simply give us the total number of particles, as we have just done in the previous case, okay, in the previous step. So this is simply the number of particles here. Okay, so the average energy comes out to be equal to 1 divided by n, the n, it is this number, okay, and then integration in the numerator from 0 to EF. Okay, and then we will substitute the value of this parameter E and GE. So E I'm clubbing with the GE, the expression for the GE. Okay, so the expression for the GE is, so it's merely the previous equation. This is basically equation 2. Okay, that is 2 into 2 pi a upon h square b square and then e square dE. Okay, so GE contains E, so when it is multiplied by E, so then that's why it's becoming E square here. Okay, so this is further equal to 1 by n. After doing the integration, when we will perform the integration, it will become E cube by 3. So when we will substitute the limits EF to 0 to EF, then it will become EF cube by 3, and the lower limits will contribute to 0. Okay, so after doing all those things, we obtain this is equal to A upon n pi h cut square b square into EF cube by 3. Okay, now we will substitute the value of EF here, and then we will obtain the desired result. Okay, so that means E at the average energy, that is equal to, so I will keep the rest of the terms outside, that is equal to A upon 3n pi h cut square b square multiply by, let's now I'm substituting the value of EF, okay, from the previously determined value in the previous step. So this one, equation 4 I mean. Okay, so it's 2 pi h cut square b square rho. Okay, 2 pi h cut square b square rho, and its power 3 by 2. Okay, because here we have substituted the value of EF from previous equation. Okay, and after doing mathematical manipulation, it comes out to be equal to 2 by 3 A by n into 2 pi h cut square b square power 1 by 2 and then rho power 3 by 2. Okay, so that's the average energy. But basically what is asked in the question, it's the average energy per unit area. Okay, and that is equal to here from, so if you bring this a on the left hand side, so then this turns out to be proportional to rho power 3 by 2. Okay, so we all the rest of the terms can be clubbed in the proportional constant of proportionality. Okay, so therefore the required option is, it's a dependency rho power 3 by 2. So yes, A is the correct option here.